Hey everybody, it's Dr. J, and today we're talking about energy. Let's talk chemistry. Alright, so today we're talking about thermochemistry, everybody. Essentially, what you need to understand about thermochemistry, this is basically the movement of energy. The movement of energy. But before we even get there, right, we got to define what energy is. So energy is basically the capacity to do work. And if you're able to do work, then you're able to produce heat. Okay. And we define work in this instance, not work as in dancing or anything like that. Work is going to be a force acting over a distance. All right. So you're applying a force over a certain area. Okay. And this is essentially how we're going to define that energy, right? Doing work and you're producing heat. Now, there's different types of energy that you guys have already probably been exposed to, right? Kinetic energy, where this is all about motion. If you guys remember the equation, Ke equals half of mass with RV squared. So when we think about kinetic energy, that's just like me walking, or if you're throwing a baseball or something like that. Thermal energy, right? That's example is hot tea. And thermal energy is all about the temperature of an object. Okay, so remember these are different types of energies, right? Potential energy, right? We always hear the example with the dam, the Hoover Dam, or any dam in that fact. All right, but basically, potential energy is dealing with the position of where you are, right? And then even chemical energy, right? This is due to those electrons and nuclei in your atoms and molecule, right? So chemical compounds, basically everything we've been talking about throughout these videos, okay? So energy, capacity to do work and produce heat. And there are many examples of energy. So a huge law in thermodynamics is the law of conservation of energy. So this is a law that you guys probably heard before, but let's define it. Energy can neither be created nor destroyed. So in a sense, energy, right, it can only be transferred. In this case, energy is constant, right? We're not going to get energy coming out of nowhere. It came from somewhere. So a good example of this is we look at this little graph here, right? So for example, we have our system energy looking, in this case, this is before the energy transfer. So what we can see here is that we're like half full in our system, and we're going to talk about what exactly a system energy is, and then we got our surroundings, right? In this case, the surroundings got up to a fourth of our full meter here. Now, after we transfer the energy between these two, what are we going to see here? Right? Well, in this example, after we transfer our energy, our surrounding energy will gain that energy we lost from our system. So we can see here, right? Our system went from half full to a quarter full. Well, where does that energy go? Right? We lost that energy. That energy did not disappear. That energy went to our surroundings. And this is all about law of conservation of energy, right? Energy isn't being created nor destroyed, so it's not coming out of anywhere, right? And it isn't disappearing. It's just being transferred in some type of way. Now, with energy, a huge unit we're going to be talking about several times going forward is joules. So joules can be defined as the amount of energy needed to move 1 kilogram of mass over a distance of 1 meter. So essentially, we have our 1 joule, but if you convert that to kilograms in mass in meters, it's going to look like this, right? Kilograms times meter squared over S squared here. Now, key thing I just want everybody to pay attention to, joules is going to be the unit for energy. That's all y'all really need to know. Okay, so joules, if you hear me talk about joules, I'm talking about energy. Okay, so joules, we talking energy here. Now, we also have a calorie. This is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so these are two different units that we're going to see see when we're talking about thermodynamics. And I got a couple of different conversion factors down here for you guys to take a look at. 1 cal equals 4.1 joules. 1 calorie or kilocalorie equals 1,000 calories or 4184 joules. And then we even got a kilowatt hour equaling our joules here. So these are some standard conversions that you might see in this energy unit. So when we're talking about energy, we must talk about internal energy. Internal energy is basically when we add up our kinetic and potential energies, right, of all of our particles in our system. Okay. Now, a key thing that we need to understand is that internal energy is what we call a state function. So this term is going to be very important going forward with thermodynamics. You want to understand state functions, right? Because there's a lot of different state functions that will be covered when you talk about thermochemistry. So before we even go further, let's define what a state function is. So a state function, this is basically, right, a way that we're going to represent a math function. Okay, so with state functions, this is what I want you to remember. Okay, state functions, we only care about the beginning and the end, right? The alpha and the omega, the initial and the final conditions, right? That's the only two things we care about when we talk about state functions, right? So we do not care about the process in between, right? We don't care what process we used or what we had to do to get to the end, right? We only care about the beginning and the end, the initial and the final. Okay. So a good example of this is like this little I like this little chart over here, the altitude. So we got a couple different pathways that we can take on this mountain here, right? In this case, right, let's say I got my guy over here, uh, guy A, and we're going to compare guy A to guy B. That would be a crazy name. Shout out to anybody that has an initial for our last name. But let's look at guy A. So guy A, he decides that he's going to take the trail, right? He's going to go up the trail, and take his time up the mountain, what I'm saying, see what's popping as he goes throughout the mountain. And we can see with this trail is kind of out the way, right? He's going up to the right, then he goes to the left. He meets another stranger. They talk a bit. Then he continues to walk up, and then he's going up, 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 up until eventually he reaches the top. Now, what we need to pay attention to is how long did it take him to get there? In this case, it took him 12 miles to actually get up this mountain. Now, the key thing with state functions, is that we said we only care about the initial and final, right, conditions. So in this case, when we're on this mountain, he starts off at 0 feet, right, with the altitude, right? We're all on the same level. But eventually, once you reach the top of the mountain, he's going to reach 10,000 feet. Cool. But let's compare him to the guy B, right? Guy B starts out at the very same 0 feet. But in this case, he looks at that trail. He says, I'm not really trying to see all that. I'm just trying to get to my destination. So he decides to take path B. So guy B is just going to go straight up the hill, no trail, a little shortcut to get to the very top at 10,000 feet. So essentially, it takes him 5 miles to get to the same destination of 10,000 feet. Now, how is this going to be a state function? Well, the key thing, and this is what I want everybody to understand with state functions, we don't care about either one of these paths, right? Both guy A and guy B started off at 0 feet, but at the end of the day, they both ended where? At 10,000 feet. He went 12 miles, he went 5 miles. Do we care? No. We only care about the beginning, 0, and the end at 10,000. Okay, and that's how we have to think about state functions. We don't care about how, right, we get to our end condition. Okay, we don't care about the process. We don't care about any of that information. We just care about the final and initial conditions. And because of this, we can use this malfunction here to help me find the change in my function. So in this case, if we're looking for the internal energy, if we're trying to find internal energy is a state function. So in order to find internal energy, all you have to do is use your final energy minus your initial energy. Okay? Because we only care about the final and initial conditions. Or if you're looking for energy change, okay, we only care about our products minus our reactants in that case, right? Because those are our beginning reactants. That's the beginning. And then that's our end, the products. So we don't care about the process, right, of how we converted our reactants to the products. We only care about those two conditions there. Okay. Now, side note, this delta here, right? This is a Greek letter. This is delta. So this isn't, don't be saying triangle. All right. This is delta, the Greek letter delta. So what exactly does that mean in chemistry? Anytime that you see this Greek letter delta, that just means that we're talking about a change. So you see delta E, right? That means that we're talking about the change in energy. So my change in energy, right, was my final energy minus my initial energy, right? Or my change in reaction energy was my products minus my energy of my reactants, right? Because this is a state function, right? Can't stress that enough. Initial and final conditions are the only thing we care about when we're talking about state functions.